All right, hello. I am John Beckman, Professor John Beckman, Dr. John Beckman. Coming to you live from Southern Command with half my brain tied behind my back. Just fair. Okay, today we have a lecture for AI in biotechnology. Although this is a little bit of a tangent, there really is not much biotechnology in this. This is a tangent lecture on a machine called the EDVAC, which is the first von Neumann machine, the first computer, the first actual computer that was built. And I'm giving this lecture now because I'm currently a master's student in a class called Advanced Computer Architectures. And Advanced Computer Architectures is essentially teaching the modern version of what this paper describes. So this material is fresh in my mind. And so while it's fresh in my mind, and as a master's student, I think it's important to read some of the most historically pertinent lore or papers from your field. If you're really interested in a field, you really have to take the time to read some of the most important historical papers. And this is one of those papers that sets up the field of computer science. So it's important for me to read this. I'll try to explain it as best I can. I understood about half of it, 50% of it, which is pretty decent and getting better. And if you're interested in these lectures, you can follow me on YouTube at Professor Beckman, Prof. Beckman. I also have Rumble and X, but most of this stuff gets posted on YouTube exclusively. So let's first just talk a little bit about the history of computer science, which will help set up the case for why you would read this paper. There's really three founding fathers of computer science. There's Turing, Shannon, and von Neumann. I can talk about the contributions briefly of each of those individuals, if I can create some space here. So Turing is really the first person to invent the computer. And Turing describes what's called the Turing Machine. So the Turing Machine is the simplest computer you can imagine. The idea is if you have a machine that has a roll of essentially paper called the tape, and the tape has two functions. It can go right and it can go left. So you imagine these old Japanese or Chinese scrolls, you can roll them to the right and you can roll them to the left. That's essentially the basis of memory in a Turing machine. So the tape is the memory. And then there are two other functions, read and write. So as this tape moves left and right, there is an arm that can write a bit, a 1 or 0, or it can read a bit, a 1 or 0. And so on this tape are bits. And what Turing describes is this machine can compute any process that is quote unquote Turing computable. Turing computable. Turing computable means it can be computed on a Turing machine. Most mathematics, most simple mathematics is Turing computable. And so it can be computed on this very simple machine. Now, when I first heard about the Turing machine, this was very complicated to me. I did not really understand this. Okay. So to help understand this a little bit more, we can talk about another founding father of computer science, Shannon, Claude Shannon. So Claude Shannon's contribution to computer science is information theory. And I still have to read Shannon's thesis, so keep that in mind. Like there's still some history that I need to do my diligence and read about. Okay, but Shannon's contribution is that he posits that all information, words, letters, signals, all information can essentially be encoded, compressed into binary, 0 or 1. So imagine, again, there's what's called ASCII code. ASCII code is where all the letters, A, B, C, have some binary representation that can be a stand-in for that letter. So imagine this is not the actual ASCII code. You'd have to look it up in a reference table. But imagine A is 0000 and B is 0001 and C is 0010, etc. On and on and on. You can see how you could create a binary code that is a stand-in for any symbol logic, any symbol. Okay, so any information can be compressed into binary. And all you need is a binary translation machine or process that will take the signal, convert it to binary, and then take the binary and reconvert it back to signal to allow that information to be transported, moved, stored, etc. That's information theory. So now if you combine information theory with the Turing machine, you can now start to understand how a computer works. A computer is compressing all the information into binary. And then a Turing machine can actually do computations by just moving the tape left and right, reading the bits, or writing new bits to store the memory. Okay? So this is the most simple computer. This is the first conceptual idea of a computer. But this is not the form of computers that people use on their desktops or their laptops. This is not a modern computer. The modern computer is in fact called a von Neumann machine, or the von Neumann architecture. And this paper that I'm talking about today is the description of the first von Neumann architecture. So let's talk now about the third founding father of computer science, John von Neumann. John von Neumann is a very interesting character. I first heard about him when reading this fantastic book, The Making of the Atomic Bomb. So when they were making the atomic bomb in Los Alamos, they flew out a bunch of genius scientists to work on making the bomb. And von Neumann was involved in that process. He was a mathematician and an engineer. And actually, von Neumann built a very key part of the atomic bomb. In the atomic bomb, there are two detonators. In Little Man, the atomic bomb had essentially a non-critical mass, what would you call it, of the fissionable material, and a smaller mass of the fissionable material. This was called the gun mechanism. And this is all public knowledge. This is all literally like in this book. This is not anything that's classified or anything like that. Okay, so don't get mad at me for just talking about what is historically in these books. It's interesting engineering. So the way that an atomic bomb explodes is you just assemble a critical mass and then the chain reaction starts and it explodes. And so the trick is that you can't let the critical mass assemble until it's ready to explode. So in the gun mechanism, the critical mass with an explosive charge shoots into the two parts shoot together. That assembles the critical mass. Okay, that's not what von Neumann worked on. Von Neumann worked on the other type of mechanism, which is the explosive lenses on a hollow ball. So instead, you assemble a hollow ball, hollow sphere of fissionable material, and then you apply explosive lenses that detonate and compress that material, pushing it inward into the critical mass to detonate the bomb. That's what von Neumann worked out. Von Neumann figured out how to do the explosive lenses that detonate the bomb. And this was the mechanism of Fat Man. So that was von Neumann's contribution to the making of the atomic bomb. So obviously, this is not a lightweight intellectual. This is one of the smartest persons that has probably ever existed on planet Earth. So after this, if that was not enough to contribute to science or contribute to the army, von Neumann goes on to then invent the first computer, the first actual modern computer, which is, again, a stunning piece of engineering. And so that is what this is, the EDVAC, which I'll talk about. And this is von Neumann with what the internet says is the first EDVAC machine, the first computer. So that's who von Neumann is. And that is the history of the three founding fathers of computer science and how they contribute. So what did von Neumann contribute and what is this EDVAC? That's what we're going to talk about. So what I did is this is kind of a long publication. I read the publication, I pulled out A, what I could understand, and B, what were the most pertinent pieces of information in my opinion. Now, much of this publication is digital logic circuits. That's more electrical engineering. So just understand that half of this publication is essentially electrical engineering, complicated electrical engineering circuits. The other half of this publication is computer architecture, which is what I am able to understand. My digital logic circuits is rusty. I did take that class. I got through it. Fine. But that knowledge is a little bit rusty. So I'll talk more about the computer architecture. So what von Neumann wants to build is a very high-speed automatic digital computing system. So not the Turing machine, not the simple tape. He wants to build a high-speed electrical computing system with logic control. That's the start of this paper. He says it's a device. Now keep in mind, like he's envisioning this, he's pulling this out of his brain. This is not something that exists. So he's literally like writing onto the paper the creation of this computing system. He says it's a device that can carry out instructions to perform calculations. And most of what they wanted to do with this is solve nonlinear partial differential equations. Or later he says some statistical experiments this could also be used for. So they want to build this fast computing system that will do these complicated calculations, very complicated calculator. And he says that instructions which govern this operation must be given to the device in absolutely exhaustive detail. This is essentially the rudimentary basics of coding. And anybody who has coded understands the syntax is very important. And that's what he's referring to with the exhaustive detail. But you should be able to give this device all the numerical information that's necessary to solve a problem, and it should be able to compute the answer. And in the past, when you would do computations or calculations, you would write these things down, on scraps of paper, and you'd store certain results, and then you'd have to compile and combine different things. So what he's envisioning is a system that will hold all those results internally and just spit out the answer. So he says those calculations will circulate in the interior of the device and never be recorded for human sensing. So it's just going to spit out the final answer. Okay, Now, here is a big important point for computer architecture. Here is the first basic components, essentially the quote unquote, the organs of a computer, of a modern computer. So here is the first written description where von Neumann describes these elements. So one of these elements, modern day computers call this an ALU, arithmetic logic unit. He calls it the CA, the central arithmetic. But just know, if you understand a little bit about computers, that's what's nowadays called the ALU, the arithmetic logic unit. So this is essentially a unit he's describing. And the function of this unit is a digital logic circuit, although they didn't have digital logic circuits when he's building this. They had vacuum tubes. But nowadays, this is a digital logic circuit hardware unit that does basic arithmetic. So you're thinking addition, he says, it's got to do addition, it's got to do subtraction, it's got to do multiplication, it's got to do division. So he's saying there needs to be this unit, the ALU or the CA, that does addition, subtraction, multiplication, and division. And each of these operations is going to be a specialized organ within this thing that does those processes. So he's envisioning we can build these little tiny organs. You send them an input and they do a function and give you the output. So he's building a system, an organ system of a brain, which is the computer. So that's the first thing you need. You need the ALU. Second, you need the logic control of the device. So you can't just send information into the ALU. You have to not only send information in, but you have to have a code that tells the ALU what to do. So you have to say, okay, with this number, I want you to add it. With this number, I want you to subtract it, etc. So there need to be operational codes, okay? And that's what's called the logic control. He calls that the CC, the control center. In modern computing, we call this the processor, or the CPU, central processing unit. This is the processor, which controls the logic and the function of the computer and the operations. So there needs to be a CPU that controls the logic, that connects to the arithmetic logic unit, that gives it the data and tells it what to do with the data. That's the second component he describes. Third, it needs to have what's called memory. He calls it M. Anytime you do a calculation, that result needs to be stored. Or if you're doing a complicated calculation, you might need to store certain results that later get combined together. So you need to have some system of memory that holds numbers, holds binary, okay? And so this is the most simple organization of a early von Neumann machine. It's got the ALU, it's got a CPU, and it's got memory. And he's describing all these things for the very first time. Two other final components to make the total component number 5. 4, it's got to have a system of input and output. He actually talks about this in biological terms, using neurons, afferent or efferent neurons from physiology, which I am also a physiology major. Afferent nerves carry sensory signals towards the central nervous system. So afferent nerves are the input, okay? So there needs to be some input, which is the afferent nerves in a brain. And efferent nerves carry motor signals away, so that's the output from the central processor. So he's understanding a little bit about biology, a little bit about the brain, and he's designing the first computer based off the structure of the brain, which is actually very interesting, especially for my biology followers. You'll find that very interesting that the first computer was largely designed based on biological principles. Okay, and then the fifth thing that's required are, I've drawn on these lines that are connecting these pieces. Modern days, we call these buses, system buses, or data buses, or control buses. These are wires or connections that carry data or control codes back and forth. These are the signals. So the input-output has to be carried via electrical signals through the buses, and he describes the buses. He says they must have organs to transfer. So again, more biological lingo. Then he says for the rest of the paper, so I've now described the 5 components that you need to make the first computer happen. Now I'm going to describe them one by one, and I'm going to tell you how to build them. It's what this guy says. He says, again, it's very interesting to read these writings because he says, just the act of writing this out will cause them to crystallize gradually until the device and its control assume a fairly definitive shape. So he's literally like, he's typing this out. He's inventing the first computer from his mind, spitting this out into the universe, which is just very interesting. Now he goes through and he defines a whole bunch of basic computer science principles. So he says it's got to rely on binary. And he describes this as there needs to be elements with discrete equilibria. That means they're either this or that, discrete equilibria, with two or more distinct states. Two would be binary, 0 or 1, which can exist indefinitely, which means it's got to hold that state. So you got to have some stable element that can switch between this or that and hold the state, okay? That's the concept of digital binary, digital memory. And I need to be able to transfer from a stimuli to tell that node to switch between this or that. So you need these nodes that can switch between this or that, and you need to be able to tell them when to switch. And he says, to build these things, to build these switches, these binary switches, you could use a few different things. You could use wheels, you could use telegraph relays, you could use electromagnets, and opening or closing of electrical circuits, which would later become digital logic circuits, combinations of these two elements, or there exists the plausible and tempting possibility of using vacuum tubes. So this is called the EDVAC, the vacuum tube. This was the first computer was built off vacuum tubes, which is no longer necessarily pertinent. That's not how they use in modern computers. But again, the interesting conceptual thing is that it doesn't need to be digital. It can be mechanical. Just has to do this or that and be controllable and discrete, binary. And he says, it's worth mentioning that neurons of higher animals, they have an all or none character. They are essentially binary nodes. So he's saying, I'm designing this based off neurons, which are 0 or 1, quiescent or excited. So he's saying the human brain is a computer, and he's going to prove it by building the first computer. Okay, more on the binary. He says, we need a system that's going to calculate decimals, but the decimals cannot be what the computer uses. So the computer can only understand the binary because the circuitry is either this or that. So it can only understand binary numbers. So we need to devise a system that will convert all numbers into binary. This is called machine code. Then the machine will handle the 0 and the 1s. And then there needs to be another conversion process where what gets output gets reconverted back into decimal. And he describes these as conversion facilities into the input and the output. So whatever you send in, you're going to send in decimal, but it's going to convert it to binary into the machine code. This is like what do we call this? This is like the compiler. He describes parallelization. He calls these telescoping operations. So he says, in order to make this thing fast, we need to carry out as many calculations simultaneously, as many as possible, which is parallelization. So some things cannot be parallelized, certain arithmetic cannot, but we're going to parallelize what we can. Then he develops a language to draw the digital logic circuits. So these are like neurons. He's drawn and he's developed his own like language system. I did not go and learn this language system. Again, like this would be something that a digital electrical engineer might be real interested in. So if you're real interested in digital logic circuits, this would be a great paper to read, to try to translate. I'm more interested in the higher level. I'm not going to go into that detail, but it's there, in there. He describes how all the calculations and the functions need to be synchronized to a clock pulse. So he's describing the first computer clock. Nowadays, we use quartz crystals, which pulse and oscillate. And there's a rising edge and a falling edge, and everything in the computer is synchronized to the clock. So he describes this. It is necessary to conceive the device as synchronous. The central clock is best thought of as an electrical oscillator, which emits every period, tau, a short standard pulse of length tau prime. So this means this computer device is going to be very large, and there's going to be all these interconnecting things. And we can't have parts of the computer get out of sync. So everything needs to be done periodically, organized like a metronome to the clock. Okay, then he starts describing some early engineering designs for memory. He starts to figure out, like, okay, if you're going to do some calculations, how many digits do you need in binary? And he calculates you need about 30 binary digits to do the calculations that he wants to do. And he says there's two ways to do this in memory. You could have one memory cell that temporally pulses 30 times 30 bits. So you could have one essentially cell that pulses, and over time, after 30 pulses, you'd get 30 bits. That's one way to do it. The other way to do it would be to have 30 cells 30, these would be called memory cells, and they all instantly pulse their bit to give you the 30-digit number instantaneously. And just for the record, this is how modern computers operate. The memory cells are parallelized, and they're all holding their number, and they're all read simultaneously. But in the old EDVAC, this is an interesting thing. In the old EDVAC, they did not actually use that. They built this temporaneous, or this time-controlled pulsing memory, which is kind of an interesting thing. But we don't do that anymore. I think that was sort of like a vacuum tube engineering decision that's now out of date. Okay, then he actually draws the logic circuits for how to build the different parts of the arithmetic logic unit. I'm not going to explain these. Okay, again, like this is digital logic circuits. But here is an adder. So here is the design of a digital logic circuit that will do addition. Then he draws later, you can look up the pictures. He does one for multiply, he does one for subtract, he does one for divide, and he does one even for square root. So he's developing a set of functions that this computer can do. And he actually draws out the digital logic circuitry that is capable of doing these arithmetic logic functions. Okay, he talks more about memory. So he's talking about how to design the memory. He's talking about memory capacity. And he says that each memory cell needs to have the value of one binary digit. So now he's doing bits, introducing bits into the digital computer. So every memory cell is going to hold a bit. And he needs to calculate, well, what is the actual capacity that I need to do the calculations that I want to do? And how should I design the memory? And he says the entire memory should be subdivided by 32 memory units. So everything computers is kind of weird. Everything computers is like a power of 2. This is where that comes from. And he does all these calculations, and he figures out, okay, how many bits am I going to need to do the calculations that I want? And he decides on the number about 65,536 bits, which is a power of 2. That's 8 kilobases. So the first computer was about 8 kilobases of memory. Okay, then he talks about the processor, how to build the processor. So in order to build the processor, you have to delineate or enumerate the very precise system of orders used in controlling the device. So you need to actually have an itemized list of every function that the computer can do. And that needs to be itemized. And each of those functions gets given what's called an opcode, and he describes the opcode. So essentially, whatever operation it's going to do, whether it's add or subtract or move something or place or read or write something in memory, it's going to have a number associated with that. So every operation, every distinct operation that the computer can do is given a number. And those numbers are stored in memory. So the way that the CPU knows what to do is that it pulls the operation codes from memory and translates them to the functionality in the arithmetic logic unit. And he even describes what's called the PC nowadays, which is a program counter and an instruction register. The program counter points to the next instruction, and he describes this. So he says the CPU should actually point to the next instruction. So it's pointing to the do this, then do this, then do this, then do this, then do this in memory. So, and these are all discrete opcodes. So the CPU is pulling opcodes from the memory in an ascending value, like an iterative value from the program counter, pulling them into the instruction register, and then telling the arithmetic logic unit what to do. So the orders come from the memory. Okay, and that's it. That's the description. So that is the most basic fundamental description of what a computer is. That's a von Neumann architecture. And all of our computers, except for quantum computers, every single computer now is based on this design. So it's worth going in and reading this and seeing the original writings and descriptions, because it's very interesting to see what they think is important. And it's also interesting to go and read these things, because if you ever want to have an impact, for example, on computer architecture, this will teach you what you need to learn. So obviously, if you really want to have an impact on computer architectures, what you need to really focus on is digital logic circuits, because 50% of this entire writing is the diagrams that are drawing out the digital logic circuits. So if that's something you're interested in, double down on that, and you can have a good skill set for hardware advances. All right, I'll stop it there. Hopefully that was interesting. Have a good day.
Let the gate be opened to die. I shall meet death head on. I shall meet death head on. Decade, you've got to get out of here. Beware foul demons and beasts, there are many foes here. The time has come to cleanse my horde. This monastery reeks with evil and corruption. Oh, I hate staining my hands with the blood of foul sorcerers. Eternal suffering would be too great for you, Diablo. Let the gate